Hello and welcome back. Now we're going to talk about the Softmax function. Now this is an activation function rather than a loss function. However, I include it here in the loss function section because it's accompanied with the cross entropy loss. So whenever you use the cross entropy loss, you're also going to use the Softmax function. Okay, that's why I included it here in this section. And actually in PyTorch, when you specify the cross entropy loss directly, it will also apply the softmax function. So you don't need to actually apply the softmax function in code. You only need to specify the cross entropy loss, and then PyTorch will take care of the rest. So the softmax function is merged with the cross entropy loss, and we're going to see that later on in this course. So basically what the softmax layer does is that it converts all your output values to a probability distribution that sums up to 1. Okay, so it turns all the class probabilities to values that sum up to 1. So let's take a look at this visualization right here. So let's say that you're classifying 3 classes, cat, dog, and zebra, for example, and you have these values from the output layer. So these are the values from your classification layer. This is for cat, this is for dog, this is for zebra. Now what we're going to do is we're going to raise each one of them to the exponential. Okay, so e to the power of negative 2.85, e to the power of 0.86, e to the power of 0.28, which is what's written right here. And we get these 3 values, 0.058, 2.36, 1.32. And then what we're going to do is we're going to normalize each value. So we're gonna take the summation of all of these values and then divide each value by this summation. Okay, so the summation of all of these values is what's written here. We're just going to sum them all up, 0.058 plus 2.36 plus 1.32, and we get 3.73. And now we're going to normalize each one of them. So we're going to divide each one of them by 3.73. And this is what's written here, 0.058 divided by 3.73, we get 0.016, and so on. If you do the calculation for the others, then you'll get what's written here, 0.631 and 0.353. Okay, now realize that these probability distributions, all of these 3 sum up to 1. So if you add them all up, 0.016 plus 0.631 plus 0.353, you get 1. So what happens here is that your output values, all of them, they get converted to probabilities that sum up to 1. Now, how is that really useful for our deep learning application? So if you take a look at this visualization here, this is a multi-class classification for the colors. So we're going to classify which color is this image, for example. Okay, and here we have our classification layer. So this is the classification layer that includes the output neurons for each class. So here the number of classes is just the number of colors that we have. And then for each output value, for each class, what we're going to do is we're going to apply the softmax function. So this is the equation of the softmax function. We do this for all the output neurons, and we get a probability distribution of our predictions. And then by taking the maximum of these probability distributions that sum up to 1, we get the predicted value. So this, for example, green is the maximum value of the probability distribution right here. Therefore, we consider green as the correct prediction. So if we go back to this example, then what's the maximum value here? It's 0.631, and therefore we consider this as the correct prediction. Okay? Now you can realize something, that why are we actually applying a softmax? We can see from the final output layers that 0.86 is actually the maximum. So why are we doing a softmax function? Now we're doing this not for testing time, we're doing this for training time. I told you that the softmax function is accompanied with the cross entropy loss. Therefore, if we're using the cross entropy loss, we need to use the softmax function. So this is for training and not for testing. Now, in training, why we need to use it after the cross entropy is because, remember, the cross entropy loss takes the logarithm of the probability. Okay, so in order to compute an efficient logarithm, you need to have a probability distribution that sums up to 1. Okay, that's why we're doing the softmax function. It's for the training. Now, during testing time, you don't need to actually compute this softmax function right here. You can just directly look at the maximum value from your output layers and take this as your prediction or your correct prediction. Okay, so let's have a look at some code. So this is the implementation of the softmax function from scratch, and this is using PyTorch. So basically, we're going to use PyTorch to verify. And there's nothing really hard about it. We're just basically doing some basic stuff like summation and division. So these are the values when you raise it to the exponential. So this is when we're applying this right here. We're raising each value to the exponential. You get these values right here. And then we're summing them all up. Okay, so the summation is torch.sum all of these values. So basically we get 7.26 summation of all of these values, and then we're going to take each value of these and divide it by 7.26. So here is where we're normalizing them, and basically we get the probability distribution that sums up to 1. Okay, so if you take, for example, this first value 2.526 and divide it by the sum, normalize it, which is 7.263, then you get 0.3479. Okay, and if you verify it here, we also have the same exact answer, 0.3479. Okay, so the sum here is the summation of all of these values, which is 7.26, and when you take each one of these values and divide it by the sum, then you get basically the probability distribution that sums up to 1. Okay, so we're going to see how this is applied in deep learning when we're doing our applications. So here we have a lot of applications we're going to talk about later on in this course. So we'll show you how to apply the cross entropy loss, which is accompanied with the softmax function. Thank you very much, and I'll see you next time.